Okay. Okay, so welcome to the last session, and our next speaker is Andrew, who's going to tell us about max coverage via simplification.
Thanks very much, Sanjeev. Thanks very much to the organizers for inviting me, and thanks for all being here on the last day. So this is a mixture of a bunch of papers, some work with my students, Hoa and David, and some more recent work with Amit and Tony Worth. So we're talking about the classic problem max coverage. So the input is M sets. If you like to think about graphs, this is like kind of M edges of a hypergraph. And each set is a subset of 1 up to n. Okay. You also have an input, an integer k, and the goal is to pick k of these sets with the largest possible maximum coverage. Okay. So I don't think an example is really necessary. But if you have the sets S1, S2, and S3, and you need to pick 2 sets, well, if you picked S1 and S2, you would cover 5 elements, and that's the optimal solution in this case. Okay, so as I said, it's a classic problem. It's NP hard, and the greedy algorithm in which you just kind of go through the sets and add, at each step, you add the set that covers the most new elements, achieves a 1 minus 1 over E approximation, and that's actually optimal. It's perhaps the simplest example of a submodular maximization problem. Okay, so over the last, I guess, almost 10 years, there's been a growing body of work on this problem and the very related set cover problem in the data stream model. Now, I'm going to specifically focus on the data stream model where the input comes as sets. So in the vanilla version of the model, like if you get the sets 1 at a time, in a slightly more fun setting, you get sets, and the sets could also disappear subsequently. So it's the kind of dynamic set model. E. Oh, Euler's constant. Yeah, that one. So the main reason I decided to talk about this material is there's some older work we had that forms the basis of the newer results, which is all about simplification. So I'm going to start off with 2 simple simplification results. One, it essentially says that if all the sets are smallish, kind of constant size, then it's possible to throw out many of the sets. So it's possible to kind of subsample the sets, basically decrease m. On the flip side, if the sets are large, it's possible to subsample the universe, subsample n, such that the sets are smallish. Now, unfortunately, this smallish isn't quite the same as that small. These are 2 separate results that you can't really combine in any natural way. So as I said, these were kind of earlier results and that we kind of are going to use for these other 2 results. I'm going to be summarizing a bunch of results for insert-only streams. The first algorithm is going to be kind of 1-pass algorithm. It uses order k space, so the dependence on n and m is only going to be kind of logarithmic. That achieves, so it's a 1-pass for arbitrary ordered streams, achieves approximation roughly half. You can get up to the magic 1 minus 1 over E if either the stream is in random order and you get 1 pass, or else if the stream is in arbitrary order, you get roughly 1 over epsilon passes. Okay. And then lastly, I'll talk about dynamic streams where these sets can be inserted and deleted. And I'll go through an algorithm that uses, again, linear in k space, like the dependence on n and m is logarithmic. It'll require multiple passes. Essentially, the number of passes is log m. If you dig into the dependencies, you have a kind of like you have this expression, but between friends, log m, and this achieves a 1 minus 1 over E minus epsilon approximation. So this is work appearing in Easter this year. It improves over a previous result by Sepper and Sanjeev by basically kind of reducing the space, removing a dependence on n. That step is fairly simple, but also kind of improving some dependencies on epsilon. And for some parameter ranges, it slightly improves on the number of passes, but not in any meaningful way. So that's my plan. Okay, so I'll start off with simplification. The the first thing I'm going to present is very simple. And it's so simple that it's a little surprising that it wasn't used in the earlier work on max coverage. But I feel like maybe I'm biased by the last 5 days, sparsification. I feel like this would be the first thing people would try these days, which is just subsample the universe. Okay, so we have these 5 sets initially with these dots representing the elements, and I'm going to subsample these dots. We sample the dots probability p, which is roughly k times 1 over epsilon squared times log m divided by opt. When I write approximation signs, I normally mean I'm throwing away constants. Sometimes I'm throwing away other things as well, but nothing morally more than constants. Okay, so after I throw away those points, those 5 sets have become sets which I'll call H of S1, H of S2, etc. Okay. Oh, opt is the value, the number of elements covered by the optimum solution. Thank you. I'll typically assume, I'll typically assume that opt is known before we do any of these sampling things. You can address this shortcoming by various tricks. Okay, so it turns out with this sampling rate, if you solve the problem with respect to the subsampled sets, you'll get a 1 plus, using any algorithm, no matter what crazy algorithm you think of. If you get an alpha approximation on the subsample set, you'll get an alpha minus epsilon approximation for the original instance. The proof of this is just everyone's favorite combination of the Chernoff bound and remembering to take the union bound over all m choose k possible ways to pick k of the m sets. Okay. Yeah.
This was already at least studied for the set counter, right?
Yeah, my understanding it was.
Exactly the same thing.
Yes. Yeah. Very much. I think when we did it, this was when we originally did it. I don't know. This idea of taking the union over all k collections was something that was specific to max coverage, as I understand it. But no, okay. This is somewhat of a warm result. It's an old result. Whether or not it was I should be throwing an extra reference there could absolutely be the case. Okay, great, thanks. So as I say, alpha approximation to the subsample universe gives you an alpha minus epsilon approximation to the original instance. And what's nice about this is that you can now assume, if you're subsampling at this rate, you can assume not only are all the sets pretty small, but you can assume the optimal solution is small. Okay, the optimal solution the optimal coverage will be k1 over epsilon squared log m, which of course implies all those sets making up the optimum solution are small. But if we want to fully leverage this, we'll want algorithms whose space depends on the size of the optimum solution rather than the size of the individual sets. The second simplification I want to talk about is slightly more complicated, but it uses ideas that have been floating around. So the idea is that we don't subsample elements here, we can color elements. Okay, we're going to apply a random hash function that takes all the elements in the universe, maps them each to a color, maps them to one of C different colors, like that. And then amongst all these sets, we'll only keep sets that have distinct collections of colors. So for example, set S1 and set S2, both of the same 4 colors. So we'll only keep one of S1 and S2, and similarly, we'll only keep one of S4 and S5. Okay. So my claim is, if you set C appropriately, you are able to throw away many of the sets, and also the optimum solution amongst the sets you keep is exactly the same as the optimum solution of the original instance. As a warm-up to this, let's assume the number of colors we use is roughly kr squared, okay, where r is the arity of the hypergraph, is the size of the maximum set. Okay, so if we're using this number of colors, then since we're remembering at most one set with each of each color value, there'll be at most this number of sets maintained. And I'll argue that amongst the sets you retain, you have an optimum solution with good probability. Okay. For this pretty large C, that's not hard to argue, and you do that as follows. So let's O1, O2, O3 up to OK be an optimum solution of your choosing. Note that because of the arity was R, and you've got K of them, the coverage of O1 up to OK is at most KR. Okay. Well, we're using that number squared. So by birthday paradox analysis, or anti-birthday paradox analysis, if you like, you can argue that all the elements covered by the optimum solution get distinct colors. Well, what's the consequence of that? Let's suppose Ri is the set retained instead of OI. So remember, we store a set with every possible collection of colors. Maybe we didn't store the optimum set OI, but we stored something else with the same set of colors. So let's call that thing Ri. Well, it's not hard to convince yourself that the colors of the points covered by R1 up to Rk is exactly the same set as the colors that you see when you look at the elements covered by O1 up to OK. The fact that R1 union R2 up to Rk, which is the kind of solution you could get, is bigger than this quantity is just by the fact that the kind of coloring of the thing was a function. And then plugging this thing and this thing together means you can argue that amongst these R sets you've collected, you will have something that covers as many things as optimum. Okay. So I said this was warm up. So it'd be nice if we could decrease the C, because then like this value is essentially kind of C to the power R. So if we decrease C, we could decrease the number of retained sets. So that's where the next idea comes from. So the idea is not just to do this not just once with one coloring, but just to do it like once, twice, 3 times, and it's going to be logarithmic number of times. Okay. So you have these T different hash functions. Actually, it suffices for these to be 2 wise hash functions. And for each coloring, so for example, oops, this first coloring here, I'll circle the sets that I'm keeping in red. Okay, so it's S2, S3, and S5. So this is a maximal collection of sets with different colors. I'll also do that for the second coloring, the third coloring, et cetera, hold up to the 10th coloring. And so now, how many different sets could I be maintaining? Well, from each coloring, I'll be maintaining C to the power R sets. And I'll be doing this T times, so it'll be T times C to the R. Okay, so the theorem is, which I'm just going to sketch how kind of like why it's true, is that if we reduce, previously it was KR all squared, so we can reduce it by a factor K. If we also set T to be logarithm K, then there's going to be this number of retained sets. So we decrease the whole thing by a factor K to the R. And yet we can still argue the maintained sets contained an optimal solution. Okay. How do we do that? Well, the general approach, and I'll dig into this in a little bit, is the proof is very adaptive. Like you can do this thing in one shot in a non-adaptive way, but I think the easiest, most natural proof is adaptive. That you fix an initial coloring, and then you argue amongst the first coloring that for each optimal set, with constant probability, you either find that optimal set or you find something that's kind of just as useful as it. Okay. And then you move on, and this just as useful means you kind of modify or you evolve your optimal kind of set, and then you argue with respect to that new optimal solution with the second coloring and then the third coloring up to the 10th coloring. So let me just dig into one step of this process. So if this is our first coloring, let's say OI is the ith set in the optimal solution again, and RI is the set retained with color RI that has the same coloring as OI. Okay, so the optimal solution in this, like, there's actually multiple optimal solutions, but maybe one optimal solution is S1, S3, and S4. Okay. And the sets that we've got with the same coloring as O1, O2, and O3, or S2, S3, and S5. So we're going to say a set OI is colorful if every element in OI gets distinct colors, and the distinct colors that OI gets are distinct from all the sets covered by the optimal solution, aside from the ones covered in OI. What you can argue is that if OI is colorful, and you replace OI by RI, this reserve set that you've sampled, then this will not change the number of elements covered. And this argument actually generalize to other functions as well. Okay, so what we need to argue is that the probability that a particular OI is colorful is moderately large, and that's something we can do. We can argue that for a given OI, the probability that set is colorful is at least, just by a mixture of union bounds and linearity of expectation, sorry, same thing, I guess, 1 minus R squared K divided by C. So this is where setting C to be K squared R, or 2 times that, gives you this. And so you're arguing that in each additional column you're considering, for every set, you've either picked up a reserve set that's just as good, or you've actually picked up the optimum set itself. So repeat this thing log K times, so basically have log K colors that you've been able to do all simultaneously initially, plug them together, and you get the result. So as I say, like when you move on to kind of subsequent colors, like kind of what you're considering as the optimum is dependent on what ends up being colorful here. Okay. So this is a kind of an evolving process. Okay. Yeah.
It's like a serious generalization of what you have for vertex cover. It's a SNP something.
Exactly. Yeah. Yeah. You can think of max coverage like in the case where kind of all the arities are 2, like K max coverage is the same as finding K disjoint edges. So yeah, it's.
Or you have to pay another R to the R factor. Yes.
Yes.
Do you know if that's necessary, or some exponential in R is necessary?
Great question. I don't know. Okay, so if I lost you at all in the previous sparsifying things, the good news is that we're going to use them as black boxes. And while it's actually true that both of those simplification processes or those sparsifying processes give you kind of state stream algorithms, I'm actually just going to kind of concentrate on algorithms that are based on the universe subsampling. Okay. So if you're with me there, you're fine. Okay, so a one-pass data stream algorithm, which is almost folklore. There's a simple, like kind of one-pass algorithm that achieves a half approximation for max coverage, assuming you know the optimal solution ahead of time. The algorithm is as follows: that you go through the sets, and if you encounter any sets that allow you to grow the number of things you've covered by opt divided by 2k new elements, you add it until you've until there are no more such sets, or until you've already added kind of k sets in this way. Simple to show this is a half approximation. If k sets gets added, each of these k sets you added this number of new elements. So k times that is at least opt divided by 2. On the flip side, if you didn't add kind of k sets, and you considered adding the optimal sets to the collection that your algorithm came up with, well, each of those optimal sets that you didn't add was ignored because it didn't cover many new elements. But all the sets you ignored cover less than opt divided by 2k. So the total amount you could grow your current solution by adding all the elements in opt is most opt divided by 2. Therefore, you've covered at least opt divided by 2 things already. So this yields a one-pass 1 over epsilon cubed k space algorithm that gives a half mass epsilon approximation. And it really is just a matter of combining this with the universe subsampling technique. You end up with an extra 1 over epsilon because you need to kind of guess opt in powers of 1 plus epsilon in this case. This is one of those few, in most cases when you have to guess opt, you can afford to guess opt until powers of 2. For this, you need to guess it up to factors of 1 plus epsilon. In preparing these slides, I actually think this can probably be reduced to 1 over epsilon squared, but I need to check the details. Okay, so that's a one-pass algorithm. Multi-pass algorithm, if you're on multiple passes, you can essentially emulate that kind of like that tried and tested greedy algorithm. Basically, in the first pass, you add all the sets that kind of cover a large number of new elements, like pass a large threshold. In the second pass, you kind of like lower the threshold a little bit. Third pass, lower the threshold a little further. Do the analysis, and you actually only need 1 over epsilon passes, where your threshold decreases by a factor 1 plus epsilon every time. And you get this result, 1 over epsilon pass, 1 minus 1 over e minus epsilon approximation using this amount of space. Okay, so the approximation factor falls by that classic 1 minus 1 over e. The space is by universe sampling, and well, I should say it's by universe sampling. And also notice that to run this algorithm, you don't need to if you've decided to add 10 different sets to your solution, you don't need to maintain those sets to keep running the algorithm. You just need to maintain the collection of things that you've covered so far. So this is why this space depends on order k, rather than saying if you've maintained t sets, and each of those sets is of size order k, you'd have maintained order tk, like you'd have had tk space. Okay. Last thing I want to briefly mention before we kind of get into the dynamic stuff is the random order algorithm. So recall that a function is submodular. A function from subsets of 1 up to m to the real numbers is submodular if for any sets x, y, and m, and I not in y, then the amount you gain by adding I to x is bigger than the amount you get from adding I to y. Okay. So it turns out there has been some work on submodular cardinality constrained monotone submodular maximization in the data stream model. And our problem is a special case of that. So it'd be natural to ask, has any of the work that's been done specifically in the random order model, does that allow us to to solve our max coverage problem in the random order model like automatically? Almost. Okay. So the issue with the work on submodular maximization in the stream is what you assume is that the elements that come in here are a permutation of 1 up to m. Okay. And you can store some collection of those elements so far, and you have oracle access to something that says what's the value of f on that subset of elements. Okay. Now, so this in the streaming setting, it would be almost as if the indices for these sets are coming in one at a time, and you don't need to bother storing those sets, but you can ask an oracle like how many elements were covered by the union of the 3rd, the 5th, and the 10th set. So again, you don't need to worry about storing those elements. It is true that now we've got the simplification result, or using the simplification result, we can adapt all these algorithms just a blow up of order k to get their approximation ratios. So an immediate corollary of the submodular results and universe sampling is a 1-pass order k squared space 1 minus 1 over e approximation. And with some more work, which I'm not going to go into, you can get this dependency kind of down to k. The main issue is that for these two algorithms here, if you're to emulate them in the context of max coverage, it wouldn't be sufficient just to keep track of what's been covered so far. You actually need to keep track of sets and potentially try different combinations of these sets as you go along. So if each of those sets is order k, and you're having to remember k of them, straightforward implementation of these is order k squared. This algorithm is just a randomized algorithm where the threshold basically decreases as you go through the stream in a discrete way. So this algorithm, actually, you can immediately get order k space, but that's only gives you a half plus something, or half minus something approximation, rather than your 1 minus 1 over e. Okay, unfortunately, I don't really have time to dig into that. What I want to finish up with talking about is results in the dynamic stream model. Okay, so we're going to need a definition. I'm going to call a set useful. It's going to be useful with respect to what I've covered so far. We're going to call a set useful if it covers opt over 2k new elements. Okay. Notice that if you give me two useful sets, S and T, if I added S to my solution, T might cease being useful. Okay. A bit annoying, but true. Okay, so the general idea for the dynamic algorithm is using a technique called sample and prune, if you've seen that before. If you haven't, that's fine. So I'm going to kind of like start off with a kind of a baby result to give a half approximation in the dynamic setting, and then I'll describe how to get the kind of the full 1 minus 1 or E approximation. So the idea is you go through one pass, and using kind of a variation of L0 sampling, you can collect, say, K sets that by themselves appear useful. Okay, so you randomly pick K such sets. And at the end of that pass, you can look at the sets that you now have in your hand. Like you'll probably add the first one, since that'll be useful. You look at the second one. Is it still useful even though you've added the first one? If it is, yeah, we'll pick it. Maybe the next one isn't. And you kind of go through these K sets, and you'll add as many as you can, as long as they each maintain this opt divided by 2, as long as they each add opt divided by 2k new elements in each step. So that's the algorithm. Okay, any questions about the algorithm? Okay. I didn't quite go into kind of quite how you sample it in the dynamic stream of these sets, but that's, as I say, a variation of L0 sampling. So the fact this is a half approximation carries over from the insert-only analysis. The space used by this algorithm is basically the space used to sample K sets. So we're going to have to run K L0 samplers. So this is where this K comes from. And the size of each sampler is going to be proportional to the number of elements in that set you're picking. Okay? Now, if you've already covered C elements at some point in the past, you need to be keeping track of these new elements. But you have this kind of quantity, the max over all the sets in the stream, like kind of the max of the elements that are not covered in all the elements in the stream. Okay. Fortunately, this could be K, and this gives you order K squared. That's a place to start. Okay. And now the sample and prune analysis comes in to establish that in each pass, one of two things happens. Like either we, at the end of the pass, either we add kind of, say, at least K over 3 new sets, which is like many of the things we sampled ends up being worth adding, or the fraction of useful sets left in the stream kind of goes down by a factor of half. I think the easiest way to see this is, and I should say, this immediately gives you log n passes, a slightly more nuanced analysis, without having to increase this thing by log factors, but just using this vanilla version allows you to shave off a log n pass, a log n. I think the simplest way to see this this result about the log n passes is via kind of this setup with an urn. You consider an urn with balls corresponding to useful sets. Okay. Think about drawing the K balls one at a time. This is going to mirror our idea of sampling kind of like useful sets as we go through the stream. I say one at a time. I think that's the helpful way to think about it, but notice by principal deferred decision, everything's going to be fine. If you look back on this after I finish the slide, everything's going to be fine if I draw on these kind of K things at the same time. Now, if we draw a useful ball, so if we sample a set that's useful and we add it to our current solution, remember what we said, some other sets that were previously useful could become unuseful. So we'll denote this. Those useful sets, those green balls have become red balls. Okay. So notice that if the fraction of balls here that are useful stay above half, and we're drawing kind of K samples from it, we'd expect K over 2 useful ball draws. And so we'd kind of, we'd expect K over 2, so we'd probably get kind of K over 3, which is what I stated in the previous kind of slide with constant probability. Now, this is the process for basically one pass. Morally, what's happening when we take a subsequent pass is that then after we've drawn the k-balls, we remove all the useless sets. We basically can remove those from consideration again. Like in subsequent passes, we only sample from sets that, when we take the pass, look useful. OK, I have 1 minute. The basic idea of improving the space complexity from k squared down to k is as follows. So we need to kind of talk about things being a slightly more nuanced notion of useful. We'll say something is V useful, a set is V useful if it covers between k and 2b new elements. And what we'll do is that in parallel, for different thresholds ranging from opt divided by 1 down to opt divided by 2k, we'll sample elements amongst that family of sets that can add so much. Okay? This is not something we're doing kind of, we're not, like, I think a natural first attempt would be to first of all try and pick up all the sets that add a lot, like until there's no sets remaining, and then move on to sets that contain like a lot divided by 2, and then a lot divided by 4, a lot divided by 8. But it turns out you can actually do this in parallel if you're clever about it. So where this helps is that the sets that add a lot are expensive to sample, but we don't need many of them. So we're actually going to, rather than sampling k sets of a certain size, we're going to sample 2 to the I sets amongst elements that add from approximately this. This allows us to decrease the space complexity of the L0 samplers to linear in k. And we're doing this thing kind of log k times in parallel. So this is one of the log k's absorbed here. And ultimately, we get that many passes. This was also achieve a factor half, but it's actually not that difficult to go all the way. Well, OK, sorry. Yeah, let me just say one thing about this slide. So to analyze this process when you've got these kind of when you've got these multiple urns in parallel, what we have is what we call a cascading urn process. So we have kind of urns with balls that correspond to useful sets with different thresholds. We're drawing 1 ball from the first, 2 balls from the next, all the way down to 2 to the power of this value from the last one. And then at the end of the pass, now remember when we had 1 urn, when we had, in the single urn process, when a set had become useless, we just removed it from all future consideration. Now, when you've got these multiple urns, a set that was like kind of contributed a lot, like kind of after you've had some previous stuff, maybe it still adds a moderate amount. So basically, balls that you remove from higher up urns need to kind of cascade down to lower urns. And so you need to do that analysis, but the analysis gives you what I claimed. The 1 minus e minus epsilon approximation is just a modification of this, combining those ideas for the multipass insert-only stream. This like kind of like this finely kind of decreasing threshold with what I've just said. So initially, for the first kind of log n passes, you do all this in parallel. You kind of find all the sets that contribute a lot, and then you move on to kind of a more careful like kind of process to kind of get once your threshold's got from opt over k, like you kind of go down and kind of like you drop the threshold very slightly at each step, and you get this result. Okay. So sorry I went 2 minutes over, but thank you very much.
I have a small technical question. A few slides ago, before the improvements, like the sampling with the I, you said you get log m passes. And why is it not log k? Yeah, at the end, because you can only have, I mean, at most 2k useful sets, right? Otherwise, you have it's
Not m useful sets.
Yeah, like if all the sets were identical, if all the like it's a really annoying stream, and every set is identical, like kind of. But the question you're asking is that like the number of useful sets is going to half in each case. Like that analysis isn't the case to take into account the fact that you actually could have been picking some useful sets. If you can balance everything, like that is where you get this. Yeah.
Since we're running a bit over time, let's take remaining questions offline. Let's thank Andrew.